Right now, somewhere in the absolute freezing darkness of the Canadian Arctic, there is a crew of drillers, and they are actively pumping ground-up walnut shells, like 3,000 feet down into solid, impenetrable rock.
Yeah, and doing it on purpose.
Right, just to stop a multi-million-dollar exploration rig from being completely swallowed alive by the Earth.
It's wild.
It is. So welcome to our deep dive. Today we are entering the invisible, incredibly high-pressure world of diamond drilling.
You know, it sounds totally absurd when you say it out loud. Walnut shells and multi-million-dollar machinery. But that is the reality of operating in an environment where your primary workspace is located a mile straight down. And you are, for all intents and purposes, completely blind.
That's the crux of it, really, because if you think about diagnostics in, well, almost any other field, we expect precision. We expect visibility.
Right, visual confirmation.
Exactly. Like if an aircraft engine is failing, a mechanic can just pull it apart, put a borescope inside, and physically look at the turbine blades. Or if a patient comes into a hospital with a broken arm, the X-ray delivers this crisp white line on a black background. The doctor points and says, you know, there's the fracture. It's visual. It's definitive.
We are so deeply comforted by that visual confirmation. I mean, modern engineering, medicine, it's all largely built around the ability to look directly at the problem. But exploration drilling strips all of that comfort away completely.
It really does.
Because the action, the friction, the geology, the potential for, catastrophic failure, it's all happening hundreds or thousands of meters below the surface. You cannot see it. You can't touch it. You are essentially trying to perform microsurgery on a patient while standing 3 blocks away.
Which brings us to the focus of today's deep dive.
Yeah.
We are looking at this highly specialized, very technical internal training document. It's simply titled Module 4 Water System.
Yeah, it's a fascinating text.
It is. It's designed to take novice drill operators and turn them into, like, masters of diagnostic problem solving. And the core premise of this manual, the thing that really hooked me, is that water isn't just a coolant in this process. It's a communication tool.
The language of the whole.
Yeah, it is literally the language that the deep earth uses to talk to the driller on the surface.
And learning to translate that language is literally the difference between discovering a billion-dollar copper deposit and permanently cementing your entire drill string into a subterranean fault line.
Oh, wow.
Yeah. This text breaks down the fluid dynamics, the pressures, the chemistry, and all the mechanical feedback loops that make up a rig's water system. It forces the operators to build this complex mental model of an invisible world based entirely on fluid behavior.
So our mission today is to extract the frameworks hidden inside this manual. Because as we trace the journey of this water, we're going to see that the lessons these drillers learn about, diagnosing invisible problems, about reading flow, managing pressure, finding structural weak points, they are absolute masterclasses in systems engineering.
Oh, absolutely.
The parallels to how we manage, say, complex supply chains or IT infrastructures or even large organizations, it's impossible to ignore.
It really is a study in navigating lagging indicators versus real-time physical feedback. The water system forces you to ask, how do you know if a system is applying productive force or if it's just generating destructive friction?
Yeah. And to understand that, we need to map the anatomy of this system first. We have to, follow the water.
Step by step.
Exactly. I want to take a ride along with a drop of fluid because it's the only way to really grasp the sheer physical gauntlet this water runs. It's this continuous high-pressure loop.
It operates very much like a cardiovascular system. And a failure at any point in the circuit compromises the entire organism. It begins at the source, which, out in the remote wilderness is rarely pristine.
Right. We aren't talking about a municipal tap here. This could be a murky boreal pond or a glacial melt river or even a recycled underground sump pit. And the manual makes a massive point right off the bat.
Definitely.
The water has to be filtered.
Highly filtered, yeah.
Because suspended silt and sand in the water, they act like liquid sandpaper. If you pull dirty water into the system, you basically accelerate the wear on every single steel, brass, and rubber component downstream.
Exactly. The suction hose is the vein pulling that raw water toward the mechanical heart of the rig. And the text emphasizes that this suction line must be as short as practically possible and perfectly airtight.
Why airtight? I mean, obviously you don't want leaks, but...
Well, the physics here are critical. The pump isn't actually pulling the water in, really. It's creating a vacuum A low pressure zone and atmospheric pressure is what pushes the water up the hose.
Oh, I see.
So if there is even a microscopic pinhole leak in that suction hose, the pump pulls air instead of water. That introduces a compressible gas into a hydraulic system. And honestly, that is the beginning of the end for high pressure drilling.
Got it. So assuming the suction line is perfectly sealed, the water hits the heart itself, the pump. This is the machine providing the kinetic energy for the entire operation. The water is forced out of the pump into a high-pressure discharge hose, and then it reaches a component called the water swivel.
The swivel.
Okay, let's unpack this, because the engineering of a water swivel is just mind-bending to me. You have this massive column of steel drill rods, maybe a mile long, weighing thousands of pounds hanging suspended in the earth, and they are rotating violently.
Very violent.
Like they can be spinning at 1,000, maybe 1,500 revolutions per minute, but the water hose connected to the top of them is totally stationary.
Right. Because if the hose rotated with the rods, it would just wrap around the rig and tear itself apart instantly.
Right. So the swivel is the mechanical joint bridging those two realities. It's kind of like a biological shoulder joint. It has to take a stationary supply of high-pressure fluid and physically inject it into the hollow center of a steel pipe that is spinning at blinding speeds.
It's incredible engineering.
It relies on these internal bearings to handle the rotational load and highly specialized mechanical seals, often made of polished ceramic or tungsten carbide.
Right. Extremely hard materials.
And they press against each other so tightly that high-pressure water can't escape, even while one face is stationary and the other is just spinning at 1,500 RPM.
And because of that, it is a massive point of vulnerability in the system. The friction generated by those mechanical seals is immense. Ironically, the seals actually rely on a microscopic film of the very water they are holding back to keep them lubricated and cool.
So if the water stops...
If the water supply stutters even a bit, those ceramic faces heat up, they crack, and they fail in a matter of seconds.
Oh, wow.
But assuming the swivel holds, the water is now inside the drill rods, and it's accelerating downward into the dark.
It plummets hundreds of meters straight down the hollow center of those steel rods until it hits the core barrel assembly at the bottom. Because the entire point of exploration drilling is to bring up a pristine cylinder of rock, the core sample for the geologists to analyze.
Right.
So the water has to navigate around this delicate inner tube holding the rock without washing the rock away.
Which brings the water to its ultimate destination and, honestly, the most violent environment in the entire system. The diamond bit.
The cutting face.
Yes. This is a matrix of metal impregnated with industrial-grade diamonds. It is being pushed into solid granite or basalt with thousands of pounds of thrust force while rotating at high speed. The friction generated down there is astronomical.
I can only imagine.
To give you an idea, steel melts at roughly 1,400 degrees Celsius. And without water, a diamond bit grinding against solid rock would reach that temperature in minutes.
It will literally weld itself to the bedrock.
Yes, exactly. It would become one with the earth. So the water erupts through these tiny channels in the bit called waterways. It flashes across the cutting face, absorbing that massive thermal load, instantly cooling the diamonds in the steel matrix.
But it has another job too, right?
Yes. It performs a second, equally vital function. As the diamonds grind the rock, they create this fine, heavy paste rock cuttings. If those cuttings stay on the bottom, the bit just regrinds the same material until it chokes.
So the water has to act like a broom. It sweeps the rock cuttings out from under the bit. But now this water is at the bottom of the hole. It's incredibly hot, and it's heavily laden with ground-up rock. It has to get all the way back to the surface.
And it can't go back up the inside of the rods because new water is rushing down.
Right. So it takes the only path left, the annulus.
The annulus. This is the critical gap between the outside of the spinning steel drill rods and the raw, uncut rock wall of the borehole itself. It's this narrow, cylindrical sleeve. The fluid is forced to turn 180 degrees at the bit and travel upward through this tight space against the pull of gravity.
And it has to travel fast. The physics of lifting rock chips against gravity dictate that the water must maintain a high annular velocity.
Right.
If the fluid moves too slowly, the heavier rock chips just simply fall out of suspension, sink back down, and bury the drill string. But if the upward flow is strong enough, the water acts like a vertical liquid escalator, carrying the debris all the way to the surface collar.
Where it flows into a settling tank.
Yeah, the heavy cuttings drop out, the water clarifies, and it gets sucked right back into the pump to do it all over again.
And that pump, the heart driving this entire closed-loop system, it warrants a much closer look. because the manual points out a fundamental misconception that trips up novice operators and seasoned engineers alike.
Oh.
Yeah. People look at a massive industrial pump and they think its job is to create pressure.
I mean, I would think that.
Right. But it does not. A pump is just a machine that converts mechanical power like from a diesel engine or an electric motor into hydraulic energy. Its sole purpose is to create flow. Yes. It is designed to move a specific volume of fluid per minute.
Right, so the pump is blind to pressure. It just wants to move the liquid forward.
Exactly. And we need to distinguish between the types of pumps the industry uses for transferring water out of a lake or, moving it between tanks on the surface. They use centrifugal pumps.
Okay.
These use a spinning impeller to throw water outward. They can move massive volumes of water very quickly, but the moment they encounter serious resistance, they slip. The water just churns inside the housing. They cannot generate the force required to push water a mile underground.
So for that, you need positive displacement.
Precisely. The gold standard in deep exploration is the triplex piston pump. It features 3 pistons, mechanically offset by 120 degrees on a heavy-duty crankshaft. When one piston is pulling water in, the other 2 are in various stages of pushing it out.
So it's
Yes. This overlapping mechanical action produces an incredibly smooth, continuous flow of water. And because it is positive displacement, every single stroke of that piston mechanically forces a fixed volume of water forward. If there is resistance, the pump doesn't slip. It just pushes harder, drawing more torque from the engine, forcing the fluid forward until something moves or something explodes.
Yikes. And there's an older design mentioned in the manual too, the duplex pump, which only has 2 cylinders.
Yeah, the duplex. Because it lacks that third overlapping piston, the flow isn't continuous. It surges. It produces a rhythmic pulsation in the fluid column.
Like a heartbeat.
Right. And in shallow drilling, that's fine. But when you are thousands of feet deep, a pulsating water column acts like a hydraulic hammer. It vibrates the delicate wireline cables, it fatigues the steel drill string, and it causes premature wear on the diamond bit. The triplex is favored because it delivers high energy with surgical smoothness.
But because it's a precision machine with a lot of moving parts, ceramic liners, high-pressure valves, tightly machined tolerances, it is highly susceptible to wear and tear. Which brings us to the maintenance and diagnostics of these massive triplex pumps. And this is where the manual introduces what they call Top Gun insights.
I love that framing.
It frames the driller like an elite fighter pilot who has to become one with the machine.
The stakes and the complexity certainly justify that analogy, honestly.
The Top Gun insight for the pump section states, listen to your pump it. It usually tells you what's wrong before the gauges do. The manual claims that veteran operators can detect a developing mechanical failure simply by hearing a change in the acoustic rhythm of the pump, or even feeling a subtle vibration through the steel deck, long before the digital pressure gauge on the control panel registers a problem.
That's the art of it.
But hold on. If we look at a modern, multi-million-dollar drill rig, they are covered in telemetry. They have digital flow meters, high-resolution pressure transducers, automated shutoffs. Why in the world would an operation rely on a guy in a hard hat listening to a metal box over reading a precision digital sensor? Isn't that just like romanticizing the past?
It sounds romantic, I'll give you that, but it is deeply grounded in the physics of mechanical failure. To understand why the ear beats the sensor, you have to understand the difference between a leading indicator and a lagging indicator.
Okay, lay it on me.
A digital pressure gauge is a lagging indicator. It measures the result of a system state. By the time a pressure gauge registers a sudden drop in pressure, a component has already failed.
It's too late.
Exactly. The valve spring has snapped, the ceramic piston liner has shattered, the high-pressure seal has blown out, the catastrophic event has occurred, and the gauge is simply reporting the aftermath.
It's the autopsy report.
Precisely. But human sensory awareness, our ability to detect microscopic shifts in acoustics and vibration functions, is a leading indicator. It detects the preconditions of failure. A triplex pump operating perfectly has a very specific hypnotic acoustic signature, a deep, rhythmic mechanical thud.
Like a steady drum beat.
Right. But imagine a tiny piece of quartz, just a grain of hard sand that made it past the filter, getting temporarily trapped under one of the stainless steel valve seats inside the pump.
It wouldn't stop the flow entirely.
No, it wouldn't alter the flow enough to register on a gauge, but it prevents that valve from sealing perfectly. So a tiny jet of high-pressure water escapes backward during the compression stroke. That escaping fluid changes the internal acoustics of the pump chamber.
Just a little bit.
Yes, it introduces a micro-hesitation in the rhythm, a slight knock,
Hmm?
a high-frequency vibration that travels down the steel flame and right into the boots of the operator standing nearby. The human brain, particularly one that has been unconsciously pattern matching that specific machine's rhythm for 12 hours a day, recognizes the anomaly instantly.
So the driller knows something is structurally wrong before the part actually breaks.
Yeah. The manual specifically notes, a pump that sounds different is rarely just having a bad day. It's asking for attention before a minor issue becomes a major failure. The human operator can stop the machine, inspect the valve, clean out the debris, and prevent a $5,000 mechanical blowout that the digital sensor would have only reported after the fact.
Man, when you scale that concept up, it becomes a phenomenal lesson in systems management. How often, in corporate structures or complex logistical operations, do leadership teams rely entirely on the digital dashboard? We look at the quarterly financial spreadsheet, or the KPI tracking software, or the automated server health reports to tell us if the organization is healthy.
And we ignore the subtle ambient acoustics of the operation. We ignore the interpersonal friction in a team meeting, or the slight increase in employee fatigue, or a subtle shift in how a client communicates. We wait for the lagging indicator, the missed quarterly target, the sudden resignation of a key engineer before we react.
Yeah. By the time it hits the spreadsheet, the valve is already broken. The driller survives by staying deeply attuned to the physical reality of the machine, not just the digital representation of it. Okay, so we've established the heart of the rig and how to listen to it. But that heart produces two distinct vital signs: pressure and flow.
The big two.
And understanding the interplay between these two forces is where the real diagnostic magic of drilling happens.
They're definitely the most commonly conflated concepts in fluid dynamics, both on the drill rig and just in general engineering. But the text is adamant that a master diagnostician must separate them completely.
Here's where it gets really interesting. The text defines pressure, which is measured in pounds per square inch, psi, or kilopascals, as nothing more than the force required to overcome resistance in a system. When water travels down that hole, it faces immense friction.
So much friction.
The sheer length of the steel pipe creates drag. The tiny millimeter-wide waterways in the diamond bit restrict the water. The thick, viscous mud in the annulus fights the upward flow. All of that is resistance, and the energy required to push through it manifests as pressure.
Right.
Flow, however, measured in gallons or liters per minute, is the actual volume of fluid moving through the system. Flow is what cools the diamonds. Flow is what physically carries the rock cuttings to the surface. Flow does the work.
To map it to an everyday physical reality, think about the plumbing in your house.
Or, better yet, a garden hose. Think about standing in your driveway with a garden hose turned on full blast. The spigot attached to your house is delivering a specific flow rate, let's say 5 gallons per minute. The water is casually spilling out the end of the open hose. The pressure is incredibly low, but the flow is high.
Right.
Now, you take your thumb and press it hard over the opening of the hose.
You have introduced a severe mechanical restriction into the system. You have created resistance.
Exactly. Suddenly the water sprays out in a violent, high-velocity jet. It feels immensely powerful. You have drastically increased the pressure in the hose. But, and this is the counterintuitive part, you haven't increased the flow at all. The spigot is still only delivering 5 gallons per minute.
Right, the volume didn't change.
In fact, by restricting the opening, your actual volumetric flow rate might have slightly decreased. You traded flow for pressure.
It is a perfect physical model. The triplex pump is the spigot providing the flow. The geology and the drill bit act as your thumb providing the resistance. A successful drilling operation requires a delicate equilibrium of both. If you have incredible flow but zero pressure, it usually means your water is just dumping out onto the ground through a broken pipe. It's not reaching the bit. But the inverse scenario is far more dangerous. Incredibly high pressure with terrible flow.
What does that look like at the bottom of the hole?
It looks like an impending disaster. High pressure with low flow means the fluid is trapped. The bit has been shoved into soft clay that has completely plugged the tiny waterways, or a piece of fractured rock has jammed inside the core barrel, blocking the fluid path. The positive displacement pump on the surface is relentlessly trying to push water down, but the water has nowhere to go.
So the resistance skyrockets,
The pressure gauge on the driller's console climbs rapidly.
but the water isn't moving.
And because it isn't moving, it isn't absorbing heat and it isn't clearing rock cuttings. If a driller looks at that high pressure gauge and thinks, wow, we've got a lot of pressure, the system is working hard, and continues to rotate the bit, they will destroy the equipment.
Just melt it down.
The text states that a bit operated under high pressure but insufficient flow will overheat, glaze the industrial diamonds, and completely melt the steel matrix in a matter of minutes. You are applying maximum force against a brick wall, generating tremendous stress but accomplishing zero productive work.
This necessitates the driller knowing exactly what the baseline resistance of their system is at all times. And the manual breaks this down into two distinct metrics: working pressure and standby pressure.
Working pressure is the dynamic reading. It is the pressure you see on the gauge when the bit is firmly pressed against the rock, actively grinding, and the fluid is pushing past the cutting face, mixing with rock dust and carrying it up the annulus. It is the total cumulative resistance of the entire active system.
So it changes over time.
Naturally. As you drill deeper and add hundreds of more feet of steel rod into the hole, the friction increases and the working pressure slowly, incrementally rises day by day.
But standby pressure isolates a critical variable.
Yes. Standby pressure is measured when the pump is running at full capacity, water is circulating all the way down and all the way back up, but the operator has mechanically lifted the drill bit a few inches off the bottom of the hole.
Ah, so it's not cutting.
The bit is not touching rock, it is freely spinning in the fluid.
You've removed the rock face from the equation entirely.
Exactly. Standby pressure tells you the inherent resistance of your plumbing infrastructure, the hoses, the rods, the annulus, without the variable of active cutting. This is your baseline diagnostic metric. By constantly comparing the standby pressure to the working pressure, an operator can mentally visualize exactly what is happening a mile underground.
Oh, that makes so much sense. If your working pressure goes up, but your standby pressure is the exact same as it was yesterday, you know the rock is changing. Maybe it got harder or the bit is getting dull.
Right.
But if you lift off the bottom and your standby pressure is suddenly 300 psi higher than it was yesterday, you have a major structural problem in your plumbing. Mud has caked onto the inside of your drill rods, narrowing the pipe, or a rubber seal has collapsed inside the barrel. The rock isn't the problem, your system is.
And because you are blind, that gauge is your only window into that reality. The Top Gun insight for this section is perhaps the most famous adage in the industry. The pressure gauge is the voice of the whole.
The voice of the whole.
Yes. But the manual explicitly warns that a master driller does not react to the static number on the gauge. A static number is meaningless without context. They react to the trend and the velocity of the change.
Right. If a driller sees the pressure gradually, slowly creeping up over a 3-hour shift, they can deduce that the cutting face of the diamond bit is slowly wearing down, becoming blunt, and requiring more force to push water past it. Or the mud in the annulus is slowly accumulating fine rock dust and becoming thicker, increasing the overall drag. It's a slow-moving degradation.
But a sudden violent spike in pressure, that is the whole screaming. A rapid spike means an instantaneous catastrophic blockage. A chunk of shattered quartz just wedged itself into the core barrel. The wall of the borehole just collapsed inward, burying the drill string under tons of rubble and choking off the annulus entirely.
So what do they do?
The manual's uncompromising here. If the pressure spikes suddenly, you disengage the clutch and stop rotation immediately. If you try to power through a sudden spike, you will twist a steel drill rod in half like a wet noodle.
And a sudden pressure drop is just as terrifying, but for the exact opposite reason.
A sudden drop means all resistance has vanished. The fluid has found a path of zero resistance. This usually indicates a catastrophic structural breach.
Like a hose bursting.
Like a high-pressure surface hose violently rupturing on the deck. Or worse, a steel rod-threaded joint snapped 1,000 meters down, and the water is simply pouring out of the broken pipe into the annulus, bypassing the bit entirely. Or the bit just drilled into a massive subterranean voida cave or an open fault line, and the water is freely dumping into the earth.
In that moment, the driller has to instantly cross-reference that sudden drop in pressure with their flow metric. They have to look at the collar of the hole where the water returns to the surface. If the pressure drops, but the water is still returning to the surface tank, they probably just snapped a rod.
Right.
But if the pressure drops and the return flow completely stops, they are pumping thousands of gallons of water into an underground cavern.
Which highlights another brilliant quote from the text. Pressure gets the headlines, flow wins the shift.
I love that. Rookie operators are obsessed with the pressure gauge because it is dynamic and dramatic. The needle is always bouncing. But veteran drillers spend their shift watching the return water flowing out of the hole. They know that as long as they have a steady volumetric flow carrying clean rock chips to the surface, the bit is cool, the hole is clean, and the system is healthy.
It is such a profound operational philosophy, and it maps so perfectly to how we evaluate performance in the business world. Think about how organizations operate. We are culturally obsessed with pressure. We look at a team pulling 80-hour weeks, dealing with intense friction, fighting through endless administrative red tape, and we look at that high pressure and think, look how hard they are working. They must be incredibly productive. We treat organizational stress like a proxy for output.
We mistake the thumb over the garden hose for actual power. We confuse the resistance with the work. Yes, you can have all the pressure in the world, the frantic emails, the back-to-back meetings, the crushing deadlines, but if the flow, the actual volume of finished productive work is restricted by a structural bottleneck, you are just redlining the system.
You're overheating the bit.
Exactly. You are generating immense heat and stress, but you aren't clearing any cuttings from the hole. The gauge looks impressive, but the bit is melting. Organizations have to focus on the return flow, not just the working pressure.
And beautifully, the manual anticipates exactly what happens when you maximize your flow, but the system still fails. Because sometimes pure water, no matter how perfectly you balance the pressure and flow, simply lacks the physical properties necessary to do the job. If the environment is hostile enough, you have to alter the fundamental chemistry of the fluid itself.
Because water is the default. It's cheap, it's ubiquitous, it's easy to pump. If you are drilling through solid, competent granite, pure water works perfectly. But the earth isn't uniform. What happens when a driller pushes through that solid granite and suddenly hits a 30-foot layer of unconsolidated sand and loose gravel?
Oh, that's a nightmare.
If you pump high-velocity pure water into a layer of loose sand, it's going to wash the sand away, the walls of the hole will instantly collapse, and it will bury your drill string in a subterranean avalanche.
Or consider the physics of lifting cuttings in a very deep, wide hole. Pure water is thin. It has a very low viscosity. If the rock cuttings are particularly dense, say, iron ore or lead zinc water, simply doesn't have the physical suspension capacity to carry them thousands of feet up against gravity.
They just fall back down.
Yeah, according to Stokes' law, which governs the settling velocity of particles in a fluid, those heavy rock chips will fall through the thin water faster than the water can lift them. They accumulate in the hole and cause a catastrophic jam. To solve these problems, the driller has to abandon pure water and engineer a complex chemical fluid known as drilling mud.
And the science of mud engineering is an entire, highly specialized discipline. The manual breaks down the primary categories, starting with the oldest and most foundational, bentonite.
Bentonite is fascinating from a chemical perspective. It is a highly colloidal, naturally occurring clay, specifically composed of a mineral called montmorillonite. It is made of microscopic, flat, hexagonal plate structures.
Okay, microscopic plates.
When you introduce bentonite powder to water, these microscopic clay plates violently attract the water molecules and physically push away from one another due to electronegative charges. The clay absorbs the water and swells to many times its original dry volume, creating a thick, highly viscous, shear thinning fluid.
The manual says it looks exactly like a thick chocolate milkshake.
Yes, and it serves two massive structural purposes. First, when you pump that thick bentonite mud down into a zone of loose sand or crumbly gravel, the pressure forces the microscopic clay particles into the porous spaces of the rock. It plasters the wall of the borehole with a tough, impermeable layer called a filter cake.
Like spreading mortar on a brick wall.
It essentially acts as a temporary, flexible cement lining, holding the fragile walls intact so you can drill through them. Second, because it is so thick, it drastically alters the physics of suspension. It can capture massive, heavy rock chips and effortlessly float them to the surface.
But there is a severe mechanical tax for using it. Because the bentonite mud is so viscous and heavy, it creates immense resistance. It massively spikes your working pressure. The triplex pump has to work much, much harder to push a chocolate milkshake a mile down a pipe than it does to push pure water.
Exactly.
And it introduces a massive variable for operator error during the mixing phase. If a driller is impatient and dumps 50 pounds of powdered bentonite into a mixing tank too quickly, the hydration kinetics fail. It creates something drillers call fish eyes.
Fish eyes are the bane of a driller's existence.
What exactly are they?
When dry clay powder hits water too fast, the outside of the clump instantly hydrates, swells, and forms an impermeable, rubbery shell around the dry powder inside. They will not mix or dissolve. You are left with hundreds of gooey, gelatinous lumps floating in your mud tank.
Ugh, that sounds awful.
And when the pump sucks those fish eyes into the system, they travel down the rods and instantly clog the microscopic waterways in the diamond bit, spiking the pressure and causing a mechanical failure.
So bentonite is powerful, but it's a blunt instrument. That's why the text moves into the modern era of fluid engineering. Polymer systems. These are completely different beasts.
Polymers are brilliant because they manipulate the physical properties of the water without adding large volumes of heavy solids to the system. We are talking about long-chain synthetic molecules, microscopic molecular noodles.
Noodles instead of plates.
When added to water, these long chains tangle together, increasing the fluid's viscosity and carrying capacity, but they don't create the massive friction drag that clay does.
They actually make the water slippery.
Exactly. They act as incredible friction reducers. In holes that are deep or highly deviated, meaning the hole isn't perfectly straight, but curves and bends, causing the steel rods to grind heavily against the rock wall, polymers provide a lubricating film that drastically drops the rotational torque.
Oh, that's clever.
Furthermore, certain polymers are designed to encapsulate the rock core sample as it enters the barrel, wrapping it in a protective chemical film so that water flow doesn't erode it before it reaches the geologist on the surface. And unlike bentonite, which leaves a permanent clay plaster on everything it touches, polymer muds can often be broken down chemically, leaving a much cleaner borehole.
The manual lists a whole pharmacy of other additives, too. You have foaming agents, which are basically industrial soaps used when a rig is drilling with compressed air instead of water, turning the groundwater into a stiff foam to lift cuttings. You have corrosion inhibitors to neutralize acidic groundwater that would otherwise rust the steel pipe from the inside out. But my absolute favorite category, because it sounds so incredibly primitive despite the high-tech context, are the lost circulation materials, or LCM.
LCMs are deployed when the driller hits a highly porous formation or fractured fault, and the drilling fluid is simply draining away into the rock. The mud needs to instantly bridge those microscopic gaps and seal the leak under immense hydraulic pressure.
And to do that, they don't use high-tech synthetic nanobots. The manual literally recommends pumping cellulose fibers, mica flakes, and ground-up walnut shells down the hole.
It sounds absurd, but the physical engineering behind it is flawless. Ground walnut shells are incredibly hard, but they aren't abrasive enough to destroy the pump valves. When thousands of tiny, jagged pieces of walnut shell are pumped into a high-pressure fracture, they act like miniature keystones in a microscopic archway.
They wedge themselves in.
They wedge themselves into the cracks. Then the flat, plate-like mica flakes stack up behind the walnut shells, acting like shingles on a roof. Finally, the thick bentonite clay pushes in behind the mica, sealing the entire bridge tight. It is an organically engineered self-assembling plug that works perfectly under extreme pressure.
It is brilliant pragmatism. But here's where I want to really dig into this. What's fascinating here is how the driller has to act as a fluid engineer, constantly balancing viscosity and density. So what does this all mean operationally? If I'm the driller and my hold is starting to collapse, or my rods are dragging with high friction, or I'm struggling to lift cuttings, the logical solution seems obvious. I just walk over to my mixing hopper and dump in a bunch of bentonite or polymer. I change the fluid to fix the problem, right?
No. And that instinct, the urge to instantly reach for a chemical solution to solve a mechanical problem, is exactly what the manual spends an entire chapter trying to deprogram out of the operator.
Yeah.
This brings us to a profound Top Gun insight, and it serves as the core operational philosophy of the entire fluid system. Mud is a tool, not a cure-all.
That makes sense.
The manual delivers a very stern warning to operators. Don't let the chemical barrel become your toolbox.
Don't let the barrel become your toolbox. That is an incredibly potent phrase.
It is deeply tempting, especially when a driller is stressed, tired, and falling behind schedule, to just throw a bag of chemicals at a problem. If the rotational torque suddenly spikes, a rookie driller might assume the hole is collapsing and immediately mix up a heavy batch of lubricating polymer mud.
Right. Greased it up.
But the manual points out that using mud to mask an undiagnosed mechanical issue is a fatal operational error. That sudden increase in torque might not be a collapsing hole at all. It might be a diamond bit that has worn completely flat. It might be a crushed bearing in the core barrel. It might be the operator applying too much downward thrust pressure.
So if the bit is dull, adding slippery mud doesn't make it cut any better. It's like taking a heavy dose of painkillers because you have a sharp rock in your shoe. The painkiller might temporarily mask the symptom, and you might feel better for an hour, but you are still structurally destroying your foot with every step. You never address the root cause.
Precisely. And in drilling, the stakes of that misdiagnosis compound exponentially. Every time an operator adds a product to the water, they fundamentally alter the entire fluid dynamic of the system.
Because it's all connected.
If they add heavy mud without confirming the actual problem, they have now made the fluid thicker. Thicker fluid requires more pressure to pump. That higher pressure puts massive strain on the triplex pump. The overstrained pump blows a high-pressure hydraulic hose on the surface, shutting down the entire operation for 2 days.
Wow.
The initial problem was a dull bit, but the chemical fix caused a catastrophic surface failure. The manual dictates that elite drillers use additives with absolute surgical purpose. They must understand the exact physical mechanism they are trying to manipulate, they measure the result immediately, and they revert to pure water the second the specific problem is mitigated. A chemical additive must solve a specific problem. It must never be used to hide one.
Okay, so we've got our triplex pump running smoothly. We've expertly balanced our working pressure against our flow rate. Our mud chemistry is dialed in perfectly to match the rock. The fluid system is under our total control. But the manual pivots drastically in Chapter 4 because it acknowledges a terrifying reality.
You can't control the environment.
Exactly. You can control the internal mechanics of the fluid, but you cannot always control the environment surrounding it. Sometimes the Earth decides to fight back.
And in exploration drilling, the environment attacks the system in two primary, devastating ways. The subterranean geology attempts to swallow the water entirely, or the surface atmosphere attempts to freeze the water solid.
Let's explore the subterranean attack first. The manual refers to this as water loss. We established that step 9 of the fluid circuit is the return flow, where the water travels back up the annulus, carrying the rock cuttings to the surface. But in a water loss scenario, you pump 100 gallons of fluid down the pipe and absolutely 0 gallons come back out.
This is terrifying.
The fluid simply vanishes into the surrounding rock formation.
It is one of the most dangerous conditions a driller can face, because maintaining that upward circulation is the only thing keeping the hole alive. If the return flow stops, the upward velocity drops to 0. All of those heavy rock cuttings that were suspended in the fluid suddenly stall, gravity takes over, and they rain back down to the bottom of the hole, packing tightly around the core barrel and the drill rods.
It's essentially burying the drill string in concrete.
Yes, it's called getting stuck. And if a string of rods gets cemented into the earth by its own cuttings, the operator might have to literally dynamite the steel off at the bottom, losing hundreds of thousands of dollars of equipment and permanently abandoning the borehole. Therefore, diagnosing a water loss scenario is a time-critical emergency.
I read this section like a detective novel. The missing water is the ultimate clue, and the driller is the detective trying to figure out where the leak is.
And just like a detective, the driller has to start by ruling out the most obvious, mundane explanations before jumping to exotic conclusions. The manual explicitly warns operators not to immediately assume the earth is swallowing the fluid.
Like, check your own equipment first.
Exactly. A burst discharge hose hidden under the rig floor, a blown ceramic seal in the water swivel, or even a loose threaded fitting on a surface pipe can easily mimic an underground water loss scenario if the driller isn't paying attention. The first step of the diagnostic framework is to rigorously rule out surface mechanical failure.
Right. You don't want to panic and pump 200 pounds of ground walnut shells a mile underground to seal a crack in the bedrock, only to realize the leak was just a loose clamp on the hose sitting 3 feet behind you.
But once the operator has verified that the surface equipment is totally secure, they must face the reality of formation loss. The drill bit has intersected a geological anomaly that is porous or fractured enough to absorb high-pressure fluid. And this is where the manual drops a Top Gun insight that completely reframes the entire concept. It states, the hole isn't always stealing your water, it might be telling you something.
This line completely shifted my perspective on the entire industry.
It is a profound paradigm shift. A novice operator sees a total loss of return water and panics. They view it purely as a mechanical crisis, a massive loss of circulation that must be violently plugged with thick mud and LCMs immediately so they can get back to drilling. But a veteran driller, and more importantly, the geologist who is paying for the hole, knows that a sudden, massive loss of water pressure marks a highly significant geological event.
Yes. If the water vanishes, it means the drill bit just punched into an open fracture, a fault zone, a shear zone, or a subterranean cavity. And in the world of mineral exploration, those structural anomalies, those exact crushed, fractured fault zones where water flows freely, are frequently the exact pathways where hydrothermal fluids deposited gold, copper, silver, or uranium millions of years ago.
The plumbing of the Earth.
The water loss isn't just a mechanical headache. It is the Earth literally drawing a giant red X on the treasure map.
The manual instructs the operator. Before trying to fix the hole, understand why the water disappeared. A master driller treats a pressure drop and water loss as incredibly valuable geological data first, and a drilling problem second. They note the exact depth, the exact pressure drop, and communicate that to the geologists, because the absence of fluid is the Earth communicating its structure through the medium of fluid dynamics.
So that is how the deep Earth fights back from below, but the atmosphere fights back from above. Chapter 4.0 is entirely dedicated to the threat of freezing, and this section reads like a survival manual.
It really does.
If a drilling operation is located in the Yukon during January or high in the Andes Mountains, the ambient temperature can drop to minus 40 degrees. And the cardinal, unforgiving rule of the entire water system is that water freezes at 0 degrees Celsius, 32 degrees Fahrenheit.
And the danger isn't simply that the water turns solid and stops flowing. The danger lies in the thermodynamics of water. When water transitions from a liquid to a solid crystalline structure, it expands in volume by approximately 9%. And it does so with terrifying, unstoppable mechanical force. It doesn't just block the equipment, it actively tears it apart from the inside out.
The analogy that came to mind immediately is leaving a sealed, full can of soda in your freezer overnight. It isn't the cold temperature that destroys the aluminum can. The cold is just a condition. It is the physical expansion of the stationary liquid inside the constrained space that causes the can to rupture and burst open.
That's a perfect way to visualize it.
And on a drill rig, that exact same physics applies to massive, solid cast iron pump housings, expensive brass check valves, and steel-braided high-pressure rubber hoses.
The manual identifies the true vulnerability with absolute clarity. Standing water is the enemy. Moving water, water that is actively circulating under high pressure, generating internal friction, and constantly moving past the heat of the engine and the friction of the bit, is incredibly difficult to freeze, even in sub-zero temperatures.
Because of all that energy.
Yes. But the very second the triplex pump is shut off and the fluid stops moving, a microscopic countdown clock begins ticking.
The freeze points are ubiquitous across the rig, the suction hose lying in the snow, the discharge hose running across the frozen deck, the water swivel suspended in the icy wind 50 feet up in the derrick, and most critically, the heavy metal housing of the pump itself.
That cast iron block.
The manual explicitly outlines the catastrophic chain of events caused by the rookie mistake of starting up a partially frozen system. If an operator engages the clutch on a pump that has a block of ice blocking the suction intake, the pump instantly starves, pulling a massive vacuum and destroying its internal seals. If the discharge hose is frozen solid, the pump attempts to push a column of water into a solid brick wall of ice.
Which is impossible.
The pressure skyrockets from 0 to 3,000 psi in a millisecond, and the weakest link in the system violently explodes.
And attempting to fix a frozen system is incredibly hazardous. The manual strictly forbids operators from using tiger torches or open flames directly on high-pressure hoses, brass valves, or pump components to thaw them out. Applying a blowtorch to a high-pressure rubber hose melts the internal synthetic seals, drastically degrades the structural integrity of the rubber, and creates a massive hidden safety hazard the next time the system is pressurized. Thawing must be done slowly, using steam or hot water.
But the real lesson here, the deep operational philosophy that stuck with me, is about individual discipline. The Top Gun insight for the freezing section says, "Winter doesn't break equipment. Water left in the wrong place does."
That is a phenomenal statement of accountability.
It completely removes the environment as an excuse. The sub-zero temperature is just an ambient condition. The actual damage, the shattered pump housing, happened because the human operator lacked the rigorous discipline to execute a proper, systematic shutdown routine. The operator finished a grueling 12-hour shift. At 3 in the morning, they were freezing, they were exhausted, they just wanted to get into the heated crew truck, and so they cut a corner.
They left the water in the pipe.
They left standing water in the pump housing, assuming it'll probably be fine until the morning shift gets here.
And by morning, the cast iron housing is cracked completely in half, the pump is destroyed, and the entire drilling operation is shut down for 4 days, waiting for a helicopter to drop a new part. Surviving extreme environments requires a relentless, almost paranoid level of operational discipline. The operator must systematically open the drain valves, bleed the hoses, blow compressed air through the swivel, and remove every drop of standing water from every exposed component every single time the circulation stops. There are no shortcuts.
If we pull that concept out of the freezing mud and apply it to our own lives or organizations, it hits incredibly hard. How often do we blame external environmental factors for our failures? We blame the bad economy, the algorithm change, a difficult client, a toxic boss, or just bad luck. We blame the winter.
It's much easier to blame the winter.
But how often was the actual root cause of our failure? Our own lack of a disciplined shutdown routine. We left emotional, administrative, or communicative standing water in the system. We didn't close the loop on a project. We avoided having that difficult, clarifying conversation with a partner. We let unresolved tensions sit quietly in a team dynamic. We left the water in the pipe. The external environment merely froze the vulnerability we left behind. We let the coal do the damage, but we were the ones who provided the water.
It is a sobering, profoundly accurate systems analysis. Organizations and relationships rarely fail solely because of the external environment. They fracture because of how the internal components were prepared and left to face that environment.
Okay, so we've navigated the earth swallowing our fluid and the sky trying to freeze it, the environment attacking the system from the outside. But the manual saves its most complex diagnostics for the final section. We're going to examine the most destructive forces on the drill rig. Invisible phenomena and hidden structural weaknesses occurring deep inside the system itself. This is segment 5, the invisible destroyers.
And the apex predator of these internal destroyers is a fluid dynamics phenomenon known as cavitation. It is widely considered one of the most mechanically damaging conditions that can afflict a high-pressure pump. And for those outside of fluid engineering, its mechanics are entirely counterintuitive.
I have to admit, before I read this document, I had no idea water could behave this way. Walk us through the physics of cavitation.
Cavitation is a catastrophic failure that originates entirely on the suction side of the pump. Recall that the pump's pistons create a vacuum to draw water from the supply tank through the suction hose. The system is designed to pull a specific volume. But imagine there is a severe restriction in that supply line.
Like what?
The filter screen at the bottom of the pond is completely choked with algae and mud. Or the suction hose has collapsed under its own weight. Or the water level in the supply tank has dropped too low. The powerful triplex pump is relentlessly trying to pull a massive volume of water, but that volume is physically unavailable. The pump is starving.
I picture it like trying to suck a highly viscous milkshake through a tiny, crushed plastic straw. You are applying maximum suction force, pulling as hard as you can with your lungs, but nothing is moving up the straw.
That is exactly the dynamic. But fluid physics dictate a severe consequence for that restriction. According to Bernoulli's principle, as the pump pulls violently against that restriction, the static pressure inside the suction line drops drastically. It drops so low, creating such an extreme vacuum that the pressure actually falls below the vapor pressure of the water.
And when water pressure drops below its vapor pressure?
The water boils.
Wait, really? It boils without heat?
It undergoes a phase change. Even if the water in the suction hose is sitting at a freezing ambient temperature of 5 degrees Celsius, the extreme low pressure causes the liquid water to instantly flash boil into vapor. This creates thousands of microscopic vacuum bubbles, or vapor cavities, inside the fluid stream.
So the pump is no longer sucking in a solid, incompressible column of liquid water. It's sucking in a frothy mix of water and microscopic vacuum bubbles.
Yes. But here is where the destruction occurs. Those low-pressure vapor bubbles travel past the intake valve and enter the internal compression chamber of the pump. A fraction of a second later, the massive steel piston reverses direction and slams forward, subjecting the chamber to extreme, explosive, high pressure, perhaps 2,000 psi.
Oh no.
The microscopic vacuum bubbles cannot survive that high-pressure environment. They collapse.
They pop.
They don't just pop, they implode violently. When a cavitation bubble implodes against a solid surface, the surrounding liquid rushes in to fill the microscopic void at supersonic speeds. This creates a microjet of water that strikes the surface with a localized pressure that can exceed tens of thousands of G-forces.
Tens of thousands from a tiny bubble.
Yes. When millions of these microscopic implosions detonate against the hardened steel valves, the brass fittings, and the ceramic liners of the pump, they generate microscopic shockwaves. The manual describes it vividly. Repeated cavitation creates tiny impact craters on metal surfaces. It literally blasts the metal away molecule by molecule, eating the pump from the inside out.
And the acoustic signature of this happening is horrifying. The manual says a cavitating pump sounds like it is physically pumping gravel. It sounds like a machine chewing rocks.
You have this massive precision-engineered metal heart violently rattling, vibrating out of rhythm, running incredibly hot, and rapidly destroying itself through millions of microscopic implosions.
And if we connect this to the bigger picture, the most profound lesson of cavitation lies in understanding exactly where the problem originated. The Top Gun insight for this section warns operators. If your pump sounds like it's chewing rocks, it probably isn't the rocks.
I see, because a novice driller hears the pump violently rattling, grinding, and vibrating, and they immediately assume the pump itself is broken. They shut down the rig, grab their wrenches, and spend 6 hours tearing the high-pressure pump apart, looking for shattered ceramic valves or broken steel pistons. But the pump isn't broken. The pump is merely the victim. The manual emphasizes over and over that cavitation almost always originates before the pump. The failure isn't occurring in the high-pressure heart. The failure is a restriction in the low-pressure supply line. It's the algae on the intake screen. It's the crushed hose. You have to look upstream to solve a downstream problem.
You cannot fix a starving heart by performing open-heart surgery on the high-pressure valves. You fix it by clearing the airway on the intake. You feed the pump the volume it requires, and it will instantly run perfectly. That concept blew me away. Look upstream to solve a downstream problem.
It applies everywhere.
Think about how universally applicable that is. How many times are we desperately trying to fix the noisy, vibrating, failing, highly visible part of our business, our software architecture, or our personal lives, when the actual root cause is a tiny, invisible restriction in the supply line far upstream? A team is missing deadlines, producing sloppy work and burning out. The manager sees the downstream failure and tries to fix it with high-pressure solutions, more oversight, stricter deadlines, performance reviews. But the team is cavitating because they are starved for resources upstream. They lack clear communication, adequate time, or proper tooling. The resulting organizational cavitation is tearing the team apart from the inside out.
It is a flawless metaphor for organizational burnout. You are demanding that the system output incredibly high pressure and high performance, but you are failing to supply it with a sufficient, unrestricted volume of resources on the intake. The system will inevitably chew itself to pieces trying to meet the demand.
Which leads us perfectly into the final and perhaps most philosophically profound diagnostic tool in the manual: pressure testing. The art of finding the weak points in a system before they fail catastrophically on their own.
Pressure testing is a highly controlled, methodical diagnostic procedure. If a driller suspects a leak, or if they have just rebuilt a section of the plumbing, they perform a test. They cap the end of the system so water cannot escape. They fill the entire circuit completely with fluid, and they use the pump to gradually, intentionally increase the pressure to a specific, extreme maximum limit.
And then they just wait.
And then they shut the pump off and watch. They watch the gauge to see if the pressure holds steady, and they physically walk the rig, inspecting every single high-pressure hose, every steel clamp, every ceramic swivel seal, and every threaded rod joint for microscopic leaks, abnormal bulges, or hairline cracks.
But I'm going to be honest, I had a massive moment of pushback when I read this section. I was thinking, hold on a second. I have a fluid system that is currently working. It's pumping water. And to test it, I am going to intentionally cap it off and jack the hydraulic pressure up to 2,000 or 3,000 psi, pushing every single component to its absolute structural limit, just to see what happens. Aren't I literally causing the damage by running the test? If I have a perfectly good rubber hose and I stress test it until it explodes, I didn't find a problem, I created one.
It is a very common, highly intuitive fear, and one that even experienced drillers struggle with. They don't want to break their own equipment. But the manual corrects this misconception beautifully with its final, definitive Top Gun insight. Pressure doesn't create weak points, it finds them.
Let me just say that again because it's brilliant. Pressure doesn't create weak points, it finds them.
The physics here are absolute. If a high-pressure, steel-braided rubber hose violently bursts on the rig floor during a controlled pressure test, it absolutely did not burst because of the test. It burst because the internal steel braiding was already rusted and compromised, or the vulcanized rubber had already severely degraded due to UV exposure. Its structural integrity was already gone.
So it was already broken.
It was a ticking time bomb. The failure was inevitable. The only variable left was when the failure would occur.
And the strategic logic here is undeniable. You want that compromised hose to violently fail on a sunny Tuesday afternoon while the rig is shut down, all the drill rods are safely pulled out of the hole and resting on the rack, and the crew is standing at a safe distance monitoring a test. You do not want that exact same hose to fail at 2 in the morning during a blinding blizzard when the diamond bit is 1,500 meters underground actively cutting rock. Because if it fails then, the sudden loss of pressure means the hole instantly collapses, the cuttings rain down, and you lose $1 million drill string.
Exactly. The purpose of the pressure test is not to prove that the system is magically indestructible. Everything breaks eventually. The goal of the test is to force the weakest link to reveal itself under highly controlled, easily managed conditions. It is the strategic revelation of truth through the application of intentional stress.
I really want to let that concept marinate because the applications are endless. Pressure testing, stress testing, non-destructive testing. We actively avoid doing this in almost every aspect of our lives because we are terrified that the test itself will cause a failure. We don't want to push a system to its limit because we don't want to see it break. But if having a difficult, high-pressure conversation breaks a relationship, the structural weakness was already there. If a sudden, unexpected surge in web traffic crashes your e-commerce platform, the bad server architecture was already there. If a minor supply chain disruption bankrupts a company, the fragile business model was already there.
Discovering your weak points on purpose in a controlled environment where you dictate the terms is an immense strategic advantage. It allows you to repair the leak, reinforce the hose, and upgrade the system on your schedule rather than waiting for the high-stakes environment to expose that flaw at the worst possible moment.
It is the ultimate diagnostic flex. You aren't passively waiting for the murky, blind realities of the whole to surprise you with a catastrophic failure. You are proactively forcing the system to demonstrate its flaws to you.
And that concept really serves as the perfect summary of the entire journey we've taken with this training manual.
It really does. We started by mapping the anatomy of the rig, following that drop of water from a murky pond, through the high-pressure heart of the triplex pump, down the spinning rods, across the melting heat of the diamond bit, and back up the annulus.
We learned to distinguish between pressure, which is merely the measurement of resistance, and flow, which is the actual kinetic work being accomplished. We look at how drillers act as underground fluid engineers, using the chemistry of bentonite clay, synthetic polymers, and ground walnut shells to manipulate the physical environment, while rigidly adhering to the philosophy that additives are a precise tool, not a cure-all, to mask bad practices.
We watched the subterranean earth fight back by swallowing our water into ancient fault zones, learning that the whole is always trying to tell us something about the geology. We saw how sub-zero temperatures exploit a lack of human discipline, proving that the winter doesn't break equipment, standing water left behind does.
And we listened to the destructive, rock-chewing acoustics of cavitation, reminding us to always look upstream for the root cause of a downstream failure.
And finally, we embraced the necessity of intentional pressure testing, knowing that pressure only finds the weak points we haven't yet addressed.
It is a masterclass in reading invisible feedback loops. The elite driller survives and succeeds by learning to translate the fluid dynamics of a water system into a highly accurate, three-dimensional physical map of a subterranean world they will never actually see.
And so we want to leave you with a final thought to mull over, a final provocation to explore in your own world. At the very beginning of this deep dive, we talked about how comforting a clean, highly visible medical X-ray is. Broken or not broken, clear and simple. But the reality is, you don't get an X-ray for your daily life. The complex systems you manage, the teams you lead, the logistical networks you build, and the relationships you nurture, they don't operate in a clean, perfectly visible laboratory. They operate in the murky, high-pressure, invisible dark, exactly like a diamond drill bit grinding away 1,000 meters underground.
You are almost always operating blind.
So, if water is the medium through which the deep earth communicates with a driller, using sudden pressure spikes, gradual flow reductions, and total fluid disappearances as its vocabulary, what are the fluid mediums in your own life? What are the invisible feedback loops, the acoustic knocks, the slight vibrations that you are currently ignoring because they haven't shown up on a dashboard yet?
What is your personal standby pressure telling you about your baseline inherent stress levels before you even engage the bit and start doing the actual work?
And perhaps most importantly, are you confusing the intense red line pressure of resistance with actual productive flow? Are you just pushing maximum force against a plug bit, generating massive heat and stress, or are you actually clearing the cuttings and making measurable progress? The digital gauges won't always tell you the truth in time. You have to learn to listen to the specific mechanical rhythm of your own pump. Take a close listen, find where you are losing circulation, and go fix the flow.